And thank you for all the attendees. We're glad you're here. So the topic that we'll be presenting, and you'll see that most of it is pre-recorded, but just a brief introduction is focused around a topic that's quite common in CAD/CAM is in-C simulation. And what we're going to show is really a newer technology and an added functionality that's possible, not just to simulate, but to create higher assurance and even improved tool paths that's possible when we look at the complete machining environment. So with that, I think we will now move into the introduction of the company and the product discussion. As Ahmet said, please enter any questions in the chat box and we'll address those at the end. Thank you. Welcome to the VDW Web Seminar for the US and Canada. I'm Alan Levine, Managing Director of OpenMind Technologies USA. I'll be presenting today along with my colleague Peter Bingman. Our topic today will be hyperMILL virtual machining, a perfect synthesis of the virtual and real worlds. Here's a brief introduction to OpenMind. We're headquartered in Germany, and locally, we oversee sales and service for North America. The team is decentralized to be close to customers and partners. The larger dots on the map are areas with more than one employee. We primarily provide direct sales and service, and there's also independent dealers in Toronto, Denver, and Houston. This is our team. We bring much experience and we deliver hyperMILL. That includes implementations, post-processors, support, training, consulting, and partner collaboration. The product has many core modules and is expanding with many options. We are 5-axis pioneers. We develop hyperMILL. Of many attributes, the key feature to our market is the tradition of innovation. Innovation is an overused word. To OpenMind, innovation is more than a word, and it's also a department in our company. We bring a different perspective to solving manufacturing problems. We will touch on a few of our innovations. Regarding technology, most people know what has been developed. Some people know how it was developed, but few people know why things have been developed. Why is where innovation occurs. Innovation is a process. One of the most impactful innovations is the development of solutions for high-performance finishing that can achieve up to 90% time reduction in many applications. The solution ultimately is about the application of barrel cutters, but we did not want to develop software for barrel cutters. We wanted to improve the machinability of surfaces. This solution is in the why category. Members of our innovation team observed large cycle times for finishing surfaces. Many CAM solutions have techniques to reduce roughing times. This only exacerbates the large finishing times. The idea of using a larger radius or barrel cutter came to mind. Then the conical barrel concept was applied to provide holder clearance and enable shorter cutter stick out. Then the process was enhanced with variable contact point, smooth links, indexing, and more. In the next step, we applied CAD techniques to reparameterize the surface and enable more parts to be machined with this process. And in a further step, After wall surfaces were optimized, they then focused on improvements to fillet machining. Another innovation is our automation center, which allows the development of scripts to reduce repetitive programming processes without requiring the use of special programming languages. The automation can cover setup, CAD, CAM, calculations, post-processing, and reports. Our automation is primarily process-oriented more than geometry-oriented. And another innovation that will be the focus of today's presentation is hyperMILL virtual machining. It is more than a post-processor or simulator. It also includes a powerful NC optimizer to improve G-code with respect to the machine environment. And there is a connected machining module that provides a bi-directional connection from CAM to CNC to the machine tool. If you enjoyed this webinar, OpenMind stores recordings of previous workshops and webinars on our website. So let's explore hyperMILL virtual machining. As mentioned, this environment includes a combination of traditional post-processing, simulation, collision detection, and the powerful NC optimizer. One aspect of the collision detection is that NC data must be confirmed in the system to be released to the machine tool. Though some programmers do not prefer this step, every manager appreciates having confirmation of NC data before it is released. The confirmation process also promotes clean and structured programming. Digital twin is a common term today. Each real piece of the manufacturing process, the machine tool, CNC, PLC, and the G-code have a one-to-one virtual representation in hyperMILL virtual machining. This makes a perfect synthesis of the real and virtual worlds. It is a true realization of what you see is what you get.
Hello, my name is Peter Bingman, and I'm going to start off with how we use our virtual machine in our programming routine. So our toolpath is first generated into NC code for the machine. The code being simulated is not quite yet released by the virtual machine until we can confirm to be collision-free. Now we can use the various buttons in the virtual machine to toggle items like toolpath graphics. I'll enable the stock removal simulation with the press of this button. We can also toggle the NC code view and access limit views to our liking. So let's go ahead and run the collision check first. So the virtual machine collision check considers all elements of the machining environment. Items such as fixtures, stock, machine components like walls, coolant manifolds, and elements that a machine component could contact another machine component. You can see on the lower right, the green button shows the NC code is collision-free in the virtual machine environments. The green button with the check approves the code to be released for physical machine. And then we'll go ahead and run our simulation to confirm that our machine will behave as we expected. In this example, we also use a smooth linking feature to prevent the tool from going to the safety position unnecessarily. Now, sometimes the programmer will run into a quick design change by the designer, and a section of the component has to be machined without a model revision. So I need to chamfer and drill a couple of holes in order to get the job out of the door. So the basic simulation, as you can see, is showing our obvious and intended collisions with our surfaces. The connection between hyperMILL and a virtual machine helps the programmer pass these intentional surface violations to assist the collision checking in our virtual machine. Go ahead and start up our virtual machine. I'll go ahead and run the collision check first before I simulate. And as you can see that the collision check shows that I do not have any violations other than what I of course intended. We can finish this job with confidence.
To recap, we plan to interfere with the part model. The hyperMILL programming parameters, such as allowance, are passed to the virtual machine, and the virtual machine passes this toolpath, and it is released for machining. The following demos highlight different aspects of the hyperMILL NC optimizer. These solutions save programming time or machining time and increase safety with detailed analysis of machine and machining conditions. Most NC simulators make a go or no-go decision. Collisions are detected, but the programmer is burdened to return to CAM to make some changes. And it's not always clear what has to be changed. Many collisions found in the hyperMILL virtual machine are avoided and solved on the spot.
So I have here in this example a set of specific machining components that have to be done. They're the 4 bosses in our basic simulation. So you can see the collision checking shows that we have some contact between the top of the part and our coolant manifold. So sticking the tool out is really not an option I'm willing to consider in this case. With the optimizer enabled, we will regenerate the NC code for the virtual machine. So the NC optimization places a small C-axis only move to avoid the collision of the part and machine coolant manifold in our final machine boss. I do not have to reprogram to fix in this scenario. And of course, no additional stick out is required. Now, there are a lot of scenarios where there can be more than one solution for our table orientation. So there can be some benefits to picking one over the other. In our toolpath, we can set a forced tilt direction to our preference. So the first video shows our part right side up, but I'm a little concerned that I will have a chip buildup situation in these holes to be machined. By setting the force direction to minus gives me my desired upside down orientation, thus eliminating my worries of a broken tool due to chip buildup. Now in this example, our simulation shows major collisions with the head on the part after collision checking is performed. But there's an alternative solution in this scenario.
The original toolpath was calculated with knowledge of the part, the cutter, and items along the spindle center line, but not the machine head. This is typical in CAM software.
Now, some sides work, some do not, but how does the programmer know? Will he have to reprogram to find the right solution? The NC optimizer will always analyze the secondary solution in a collision condition. This eliminates the need for the programmer to guess which direction to go. Our code is collision checked, has been found collision free, and is approved for the machine.
The best solution variant is selected automatically. These decision points can occur many times in a workpiece, and a manual approach would be time-consuming and error-prone.
So now in this example, our first simulation shows us a warning that our machine violates the axis limits of this machine. I'll use the feed rate knob to increase the speed of our simulation. Now, the part can theoretically fit into the machine work envelope, but the programmer's tasked with trying to solve this issue. Does he need to make unique work holding? Our next simulation shows the result with the NC optimizer. The NC optimizer will utilize the larger section of the linear travel in the X direction. So before the limit can be reached, the NC optimization kicks in and rotates the C axis to keep the workpiece in the workspace. You'll also see with my zoom in here on the C axis move, it shows a subtle path blend in order to eliminate any potential witness lines. This blend can, of course, be defined to the user's liking. Now, upon first inspection, we see a list of collisions in our information tab after our collision check is performed. When the simulation plays, the collisions are pretty obvious. We cannot rough out the part in one tool path due to the offset component of the head. So how do we solve this? Do we split the tool path and do all of the programming work to shift the head in multiple orientations, track the stock to make sure we didn't miss anything? This is a lot of work. When the NC optimization is performed in the post run, it sees that we can machine 3 of these 4 sides and then will automatically rotate the C axis to avoid collision with our machine head. This will happen every time the NC optimizer will see a collision. In this roughing operation, the C axis will shift in each step down. In the next example, we're trying to use a simultaneous path to machine the outer part of this middle component. Now, it's pretty obvious in the simulation that with the limited C axis on the machine runs out of travel. Our 5-axis options are somewhat limited, but how to overcome this obstacle in this application? Now, again, the programmer can create path splits, tilt orientations, but the goal is to minimize the programming time. With a simple checkbox, we can use the optimizer to implement automatic rewinding in order to prevent the limit switch on the C-axis head machine. You can see in the post run, the optimizer is used. It will insert 2 rewinds into our NC program.
Those red lines show a trace of the cutter tip during the rewinds that we will see. It looks like a large rewind, but in reality, watch the pivot axis, which is essentially still.
That's right. So not only does the virtual machine NC optimizer assist us with the rewind, it also pre-winds the C axis to get as much of the travel as it can before the rewind takes place. This is a very nice cherry on the top of an already great function of the virtual machine. As you can see, our 2 full revolutions. Now, as I zoom in on the tool path, you can see the blending of the tool path to avoid any witness line where the part picks up, then comes back down to finish the cut.
This is a presentation of 6-axis knife cutting for the cutting of honeycomb composites. Composites are a high-performance, lightweight structural material. They're crucial in aerospace applications where performance is measured by weight reduction. The cutting process is primarily trimming shapes with a swarf toolpath. This material is best cut with an ultrasonic knife. The cutting is with a high-frequency axial oscillation of about 30 microns or 1 thou. To manage the knife orientation, the spindle also becomes a programmable axis, and thus we need 6-axis commands. hyperMILL computes a typical 5-axis toolpath with swarf and cutter offsets and other technology parameters for the honeycomb. The virtual machine optimizer considers the machine characteristics and develops the 6-axis output. The result you see is a super clean cut. So hyperMILL virtual machining helps you. It's a post-simulator detailed collision check and optimizer, full modeling of the machine environment, improved solutions without reverting back to CAM. Virtual machining saves you by reduced programming time, reduced prove-outs, and reduced machining time. In summary, you have increased confidence and lower risk. For more information, use the listed contact data. At this point, we'll return for some question and answer.
Thank you very much, Mr. Levine, for this informative insights. Now we have time for questions from the participants. Dear attendees, type your questions into the question window now. What other aspects of the topic are you interested in? What can Mr. Levine explain to you in more detail? Take this opportunity. Thank you.
Thanks, Amit. Let me review the chat window, and again, please add to enter your own questions. Let's see what we got so far. So there's a question: is the hyperMILL virtual machine simulating the actual G code, meaning the code on the machine? So the answer would be yes. That actually many simulators are simulating a neutral file. We're actually simulating the G code, and more precisely, we simulate something syntactically equivalent. But because we want to save the releasing of the file until after you confirm it. So in that case, we are simulating G code of the CAM software and also the machine elements. Together with that confidence, we release the file and the G code can be sent to the machine. That's great. Another question, please give me some specific examples of opportunities where I can save machining time based on the virtual machine. I guess there's a variety of ideas. We showed some programming savings, but also for machining time savings, you saw in some of the demos, smooth linking connections. It looks like little loops. The typical machining process would have a direct retract. The machine stops, synchronizes, reconnects, stops, synchronizes, and re-enters in the part. These smooth linking moves will save you about as much as 10 or 20%, depending on what your reference material is. If you're cutting in aluminum where the cut time is fast, then saving the air time is high potential. Another area I don't know that we emphasize is that we also during the demonstrations, we also were able to change a clearance plane. And by changing the clearance plane, we're able to keep it closer to the part with full collision protection. On some parts, you want a different collision, different clearance plane for each area. This system will look at that for you. Let's see what else we got. Customer says, "What is there anything special I need on my machine control to support the virtual machine and the NC optimizer. The short answer would be what's called a tool center point control. This is a capability common on most 5-axis machines today, especially Heidenhain and Siemens, but also Fanuc, MAXX, Haas, Puma, and Rotary as examples. The optimizer is tracking a lot of the tool tip, and using the tool center point on the machine control, you are able to also control the tool tip. So these work hand in hand. Let's see, the next question. I don't have a complex head style machine, the ones we showed with the large offset heads where collision is a big issue. Can I still obtain benefits from the optimizer? And the answer, yes. And I think we already addressed that a bit in an earlier question about the linking and clearance planes. So these will help you further. I think it was the first demo where there were 4 bosses and we hit a coolant manifold. So a fairly simple machine, but realistically, no machine is perfectly symmetric. We want to check all of these items. Most likely they weren't checked in the CAM software, whether hyperMILL or any other CAM software. The next question. I run a large gantry mill, and it has what they call a earth gear, which, if you're not familiar, is to keep the high power in the cutting. It may be every 2 or 5 degrees. There's fixed positions, and there's a clamping system to hold the machine in place. And we support earth gear style machines. And the answer is yes. So this indexing style is easy to control, but even more valuable is that not every position is possible for machining. So we can use the virtual machine, identify the earth gear potential solutions, and then copy through a clipboard and put them back into hyperMILL and make sure that the programming is going to match the simulation. So that's a nice benefit. And it looks like maybe a little more time, one more question. In the case where you do have collisions, what do I do as a user? And the answer is, it depends a bit. In some cases, we're able to solve these conditions within the virtual machine, so you don't have to send a programmer back to the toolpath generation. In those systems, when you send the programmer back to toolpath, you don't always know the programmer doesn't know what he has to fix. He knows there's a problem. So in as many cases as possible, we're identifying the solutions. If it has to do with rotating a C-axis, for example, this will help us to alleviate some problems. In other cases, we can change an allowance that a few thousandths of an inch is an acceptable error if it's a small fillet, for example, or a small collision with a fillet. So in these situations, there's capability where you can release from a gouge to a collision and then to a contact, which you may choose to call acceptable. For the moment, I think we're done with questions. So Ahmet, I can give it back to you.
Yes, thank you. Alan, have you final words to our attendees?
Sure. Well, certainly we thank you for your time and your interest in this technology that we've developed and we're bringing into the market. We think it's making a really big impact in many cases. Right now, our focus is 5-axis machines, which are quite common. The integrated solutions working well with all machines, but especially German machines and German controls like Heidenhain and Siemens and Rotary. So we thank you again for your time today. Your time is valuable. If you have other questions, of course, feel free to contact us at any time. Thanks again.
Thank you very much for this interesting session, and also the attendees. Thank you very much for your attention. In the coming presentation, the speaker, Andre Hildebrand, will show you how the technology can change the production environments through cold rolling profile parts. And that sounds good, doesn't it? I think it is better that you do not miss the presentation. And goodbye, and Stay safe.
Bye now. Have a great day.
Bye.